we begin with a definition. Let f from a to r be a function. We say f is continuous if, as to be expected, f is continuous at each point x in A. So a function that is continuous at each point of the set is known as a continuous function. Now what we want to do is we want to consider functions that are globally continuous. That means throughout their domain A. At every point in their domain they're continuous, and I want to see whether I can characterize this in some way. So to do that, first let me state a proposition. Let f from A to R be continuous at x in A, at just one point. Then consider b f of x epsilon. So consider a ball of radius epsilon around the point f of x. We can find, or rather let me, instead of writing consider, then for each ball b f of x epsilon, we can find a ball b x delta such that f of b x delta intersect with A is a subset of b of f of x epsilon. Look at the point f of x, consider a ball b of f of x epsilon. We can find a ball bx delta, of course delta greater than 0, such that f of bx delta intersect A is contained in b of f of x epsilon. Again, here also let me just mention epsilon is also greater than 0. Proof. This is just a highly complicated way of stating the epsilon delta criterion, right? Think. So this fancy proposition just recasts the epsilon delta definition in the language of balls. Now, why is this recast into the language of balls useful? Because we can prove the following theorem. The importance of this theorem will not be clear to you until you do a course in topology, but since this is so important, I am stating it now. Let f from AB, now I am fixing an open set, to R be a function. Then f is continuous if and only if for each open set U subset of R, the inverse image f inverse of U, just recall this is nothing but x in AB such that f of x is an element of U. This is the pre-image or the inverse image. Please again do not confuse this with the inverse of a function. This is going to be a set. F inverse of U is an open set. Okay. Let's prove this theorem. Proof. Suppose f is continuous. F is continuous and U subset of R is open. If F inverse U is the empty set, this is a reasonable possibility. The function f need not attain any value in the set U. That is very much possible. If f inverse U is the empty set, then nothing to prove. Why? Because the empty set, for extraordinarily stupid reasons, is an open set. The condition of open set is every point is an interior point. There is no point in the empty set. Therefore, it's an open set for stupid reasons. There's nothing to prove. Okay? Let X be an element of F inverse U. We are assuming now that F inverse U is a non-empty set. Suffices to show that X is an interior point of F inverse U. Right? That's the definition of an open set. Every point is an interior point. Okay. Now what we do is, by the previous proposition, if we choose epsilon greater than 0 such that B epsilon wrong notation, B f of x epsilon is contained in U, which we can do because f of x is an element of U and U is an open set, then we can find delta greater than 0 such that f of B x delta intersect A, not A, the notation changed in this particular theorem, intersect the open interval AB is a subset of B f of x epsilon. Right? This is exactly what the previous proposition said. F of bx delta intersect A is subset of B of fx epsilon. Right? Note that this is contained in U. That's how we chose our epsilon. We chose our epsilon in such a manner that B of f of x epsilon is contained in U. But since AB itself is open, we can shrink delta to ensure Bx delta is contained in the open set AB. This can be done. Once you do that, what we get is Bx delta intersect AB. Well, no shock here, it's just Bx delta, because we have shrunk delta to assume that Bx delta is contained in AB. Now, immediately this plus this gives f of Bx delta is contained in B of f of x epsilon is contained in U. Right? But this means B of x delta is a subset of f inverse U. In other words, x is an interior point. Hence, x is an interior point of f inverse U. And we are done. Okay. So this proves one direction. Assuming f is continuous, we got this. Now conversely, assume that U subset of R is open, we have F inverse U to be open. Okay, then for X in AB we can choose for any fixed epsilon greater than 0, U has B of X epsilon, right? Because this applies to any open set, it certainly applies to open balls. Okay, then F inverse Bx epsilon is open. In other words, sorry, not X epsilon, sorry about this, F of X epsilon. This has to be on the codomain side, not on the domain side. B of Fx epsilon, B of Fx epsilon is open. In other words, X is an interior point of F inverse B F of X epsilon. Therefore we can find delta greater than 0 such that B of X delta is contained in F inverse B F of X epsilon, which is just saying F of Bx delta is contained in B of F of X epsilon. Okay, that by the previous proposition we are done. By the previous proposition we are done. So what does this say? This theorem says that if you are starting with a function from an open interval, then the function f is continuous if and only if it pulls back open sets in R to open sets. Okay. Now, if you think about this for a moment, if you look through the proof carefully, this AB could have been replaced by any open set. And the same proof will go through with minor modifications. Please think about that. Okay, so let me just mention that this is called the topological categorization of continuity. Topological characterization of continuity. Okay. This is a course on real analysis, and you have just watched the module on global continuity and open sets.